This lecture deals with bivariate relationships, that is, relationships between two variables, and it's organized into two parts. Part 1 deals with bivariate tables, also known as crosstabs or contingency tables, and properties of bivariate relationships, including the existence of a relationship, the strength, and direction. Part 2 deals with the elaboration process, or a way of looking to see if a third variable influences the relationship between any given set of two variables. So what is a bivariate table? A bivariate table is one that's constructed by classifying cases according to their joint distribution on two variables. You can kind of think of it like two univariate tables joined together. And like most tables that we've seen, bivariate tables have several essential features that alert people to their contents. Here's a stylized image of a bivariate table. Let's look to see what are the essential features of this table. First, we have some kind of descriptive title telling people what information is being conveyed in the table. Second, notice that the table has two dimensions, one for the independent variable and another for the dependent variable. Typically, the categories of the independent variable are put in the columns of the table, and categories of the dependent variable are put into rows. Incidentally, tables are typically named according to their number of rows and number of columns. So for example, a 2x2 table has 2 rows and 2 columns. Cells indicate the intersection of rows and columns, and they contain information on either the percent or frequency of cases falling into each cross-classified category, the independent and dependent variable. Another feature of the table is it contains row and column totals, or marginals, because they're found at the margins of the tables. And they tell us basically the number of cases falling into each category of each of the variables. We also have an overall total, or row total. And we have a data source indicating where the information come from originally. Let's look at an example of a bivariate table, looking at the relationship between highest degree earned and sex. In this example, degree is the dependent variable, and sex is the independent variable. So here's what the table looks like. Notice that the columns include the values of the independent variable, in this case sex, and so males and females are arrayed down the columns. The values of the dependent variable, degree, are arrayed along the rows. So people here are described according to whether they have a less than high school degree, junior college, bachelor's, or graduate degree. The cells show the intersection of the independent and dependent variables. Basically, the different combinations of males and females at different degrees. How do we interpret these numbers? Well, we can start by looking at the number of males who have a less than high school education. And we can see from the table that there's 135 males with less than a high school education. And likewise, we can interpret any of the other combinations of males and females at different terminal degrees. Notice also that we have row and column totals. These are like the univariate distribution of both variables. So for example, we can see that 288 people have less than a high school degree. 976 people have a high school degree. 151 have a junior college degree, and so on. Likewise, we can see that there are 886 males and 1,088 females. And then we have a total number of cases, in this case, 1,974. One reason that we create bivariate tables is to see whether there's some kind of a relationship between the independent and dependent variable. And we can facilitate the interpretation of that effect by converting the frequencies in tables into percentages. Now we have several different percentages that we could choose from. For example, we could create row percentages, or column percentages, or even overall percentages. Which of these should we choose, however? Which would make the pattern most obvious? Well, by convention, percentages are usually calculated within the categories of the independent variable. In other words, we calculate column percentages. Creating column percentages allows us to see the different effect of the independent variable for any given value of the dependent variable. To see this, let's consider again the example of the relationship between sex and highest degree earned. So you can see here, this is our frequency table, the same one that we saw earlier. How do we convert these frequencies into percentages? Well, let's just take a look at one of the frequencies, returning again to the number of males who have less than a high school degree. If we take the frequency of males in that category and we divide it by the column total and then multiply that value by 100, that gives us the percent of cases that are in that category. In this case, it comes out to 15.24%. In like fashion, we can create percentages for all the different categories of the variables by dividing each of the cell frequencies by their respective column total and then multiplying it by 100. And the same goes for the total overall column. So notice that we can now interpret the difference between, for any given value of the dependent variable, the percent of men and women falling into that category. And so here you can see that whereas 15.24% of men have less than a high school education, only 14% of women, 14.06% to be specific, have less than high school education. And so you can see that there's somewhat of a difference between men and women with respect to this category. Likewise, we could look at the difference between men and women across all the different categories to get a sense of whether there's a relationship between these two variables. So these bivariate tables or crosstabs tell us three things about a bivariate relationship. One, whether there's any relationship at all. Two, the strength of that relationship. And three, the direction of the relationship. Let's consider each of these in turn. Starting with the existence of a relationship. How do we determine it? Well, we basically look at the percentages across the categories of the independent variable. If the percentages differ, that implies there's some kind of a relationship. But if they don't differ, that is, if the same proportion of cases are found for one category of the independent variable as the other, the difference therefore would be 0, and that implies that there's no relationship. So let's return again to our percent distribution of the relationship between highest degree earned and sex. Is there a relationship here? How do we know? Well, we could look at any given category, and we could ask whether there's any kind of a percent difference between males and females falling into that category. Here we see that again, 15.24% of men have less than a high school degree, only 14.06% of women have less than a high school degree. If we subtract that difference, 15.24 minus 14.06, we notice that the difference isn't 0, and that implies that there's some kind of relationship between this variable. Now, this is only a rough sense of whether there's a relationship, and ideally we'd want to look at every category to see if there's differences. What about the strength of the relationship? Well, again, if we look at the percent differences, the magnitude of that difference gives us a rough indicator of how strong that relationship is. In general, the larger the percent differences, the stronger the relationship, and the smaller that difference, the weaker the relationship. We can also assess whether there's some kind of direction in the relationship. However, this is only done for variables that are measured at an ordinal level or higher, because these are the only variables that have any kind of rank ordering. In other words, we can't say anything about the direction of the relationship for nominal variables. There's basically two kinds of relationships that we could find in terms of direction. First, we could have a positive relationship, and that means that the variables kind of change together. High values of one variable are going with high values of the other, and vice versa. Alternatively, there may be a negative relationship, which means that as we increase the values of one variable, the values of the other variable actually decrease. Let's take a look at another example. This table shows us the relationship between the bivariate distribution of mothers and fathers' highest degree earned. Can we say something about the direction of the relationship? Well, notice that we have two variables that are measured on an ordinal level of measurement. And so yes, in this case, we can say something about the direction. So how do we figure out direction? Well, first of all, we have to figure out where the positive and negative relationship is on this table. In order to do that, we basically ignore the actual contents of the cell. We only pay attention to the actual categories of the variable. And what we have to do is we have to identify the high and the low categories for both. So you can see that less than high school is the low category for highest degree, while graduate is the high category. So that means that in the upper left-hand corner, we have the low values for both variables. And in the lower right-hand corner, we have the high values for both variables. So that means that the positive direction in this table is going from the upper left-hand corner to the lower right-hand corner, because this is where, as low values of school for both are going to high on both. In other words, this is where we find that as we're going from more low-educated mothers to more high-educated mothers, we're also finding that same pattern for fathers. That is, both fathers and mothers' education is going from low categories to high categories, and that's a positive relationship. What about a negative relationship? Well, that's the opposite direction. So if we look from the lower left-hand corner to the upper right-hand corner, we're seeing that values of father's highest degree are going with the low values of mother's highest degree, and vice versa. And so that's a negative direction. Now, what about the actual relationship in our table? Does this table show a negative or a positive relationship? Well, if we go back to our actual data and pay attention to it now, we can determine that. So here what I've done is I've taken each of the columns and I've identified the highest percent in each column. And so notice that the less than high school for mothers, less than high school for fathers is the highest category in the first column. For the second column, high school degree for both is the highest. For the third column, it looks like the highest category is mothers who have a junior college degree and fathers who have a high school degree. That makes up 49.43% of that column. If we do this exercise for every single column, we can get an overall sense of the overall pattern in the data. And so it looks like what we're finding is that the highest percentages seem to be on the diagonal running from the upper left-hand corner to the lower right-hand corner. And again, that's a positive relationship, because what we're seeing is that there's a tendency for mothers who have less education to be related to fathers who have less education, and for mothers who have high education to be related to fathers who have high education. So therefore, this is a positive relationship. And so here again, we're seeing low values and high values of the two variables going together. In other words, as father's education goes up, so does mother's education, and that implies a positive association.